Thanks for the introduction. I'm Jang-Sup Shin from Seoul National University, and today I'm going to talk about CRCount, our work, which is about using reference counting to mitigate use after free vulnerabilities in legacy C or C++ programs. Pointers. Do you have the remote? Okay, sorry about that. So there have been recently many use after free vulnerabilities reported, and there has also been many works which try to mitigate these vulnerabilities. So I think many of you are already familiar with these vulnerabilities, so I'll just briefly explain what they are and how they can be exploited by the attackers. So first, there is this figure that object B's next pointer is pointing to object A, and next object A is freed, but the pointers does not change, so the object B's next pointer still points to the same location. Here, the object B's next pointer is referred to as the dangling pointer because the object A is freed, but object B's next pointer still holds the address of the object A. And in figure C, object X is newly allocated, and suppose that the attacker can control the values of object X. And suppose that the attacker writes arbitrary integer data at the location which previously held the object A's next pointer. Later in the program, object B's next pointer can be dereferenced, and at this point, it is called the use after free vulnerability because object B's next pointer, which is a dangling pointer, is dereferenced after the object has been freed. So at that point, when the object B's next pointer is dereferenced, the program may think that object A's next pointer is still valid and further dereference it based on the attacker provided value. Then the attacker effectively has the arbitrary memory access capability. So to mitigate these kind of errors, there have been many works recently, but in this presentation, I'm going to introduce two of those works, which are most relevant to our work. So the first one is called CETS, and we categorize it as an access validation approach. And in their approach, when the object is allocated, they allocate a lock for the object at the separate memory location. And for the pointer, they associate two metadata, and the one is the lock address, which points to the lock for the object. And the other is the key, which is also stored to the lock for the object. And whenever the pointer is copied, they propagate the pointer metadata associated with the pointers. When the object is freed, they set the key at the lock location to the invalid value. So later, whenever the pointer is dereferenced, they look at the pointer metadata and they look at the lock address, and they compare the key held by the lock address with the key held by the pointer. So if those two values does not match, it means that the use after free has been detected. So in this way, they can detect the use after free errors, but the disadvantage is that they need to perform this kind of checks on every memory access. So it incurs a significant memory overhead. The runtime overhead. So the next work is called Dangling, and we categorize this approach as a pointer invalidation approach. So what they do is that for each heap object, they maintain a list of locations of pointers to the object. So whenever the pointer is stored in memory or copied in memory, they record this to the list for the object. So after that, when the object is freed, they go over this list and see if that pointer still points to the object, and if so, they invalidate the pointers. So later, when the dangling pointers are dereferenced, even though they do not perform any kind of checks, since the pointer is already invalidated, it will automatically result in memory access fault. So in this way, they do not have to perform any checks perform checks on every memory access, thus thereby reducing runtime overhead. But these list of pointers can grow quite large, especially for the pointer-intensive programs. So the memory overhead for spec benchmark is over 100%, and also the runtime is still 44% overhead, which is it can be acceptable for testing purposes, but it's not really acceptable for runtime protection. So in this work, we try to use the reference counting to mitigate use after freeze in legacy programs. And here, this example, I'm trying to show how use after freeze can be mitigated with the reference count. So in this example, after line 7, object B's next pointer points to object A, and also the pointer A points to object A. So the reference count of object A is 2. After line 11, object A is freed, but the pointer's value does not change, so the reference count stays the same. And after line 15, pointer A now points to the other object, so the reference count is decreased to 1. So we can insert some kind of API call right before this operation to reduce the reference count. And after line 16, object B is freed, and we can see the type of the pointer B, and we can see that there is a next pointer in the object B. So we can invalidate the object B's next pointer and decrease the reference count for object A. So far, it seems very trivial to apply this kind of reference counting to mitigate use after freeze. But of course, as always, we have challenges when we want to apply this reference counting to legacy C programs. And this slightly more complex example shows the challenges for applying reference counting to legacy programs. So the difference with the previous example is that object B is not created directly from malloc core, but instead the large chunk of memory is allocated first, and the object B is created by setting the pointer B in the middle of the chunk. And also the object C is not a struct type, but it is a union type, so the next pointer and the data field shares the same memory location. So after line 10, here, object B's next pointer and object C's next pointer, and pointer A points to object A, so the reference count is 3. And after line 15, object A is freed and pointer A is set to null value. So you can decrease the reference count to 2. And here, after 19, the chunk is freed, but the problem here is that the chunk's type is only the character array, so we do not know if any pointers are included in the chunk. So here's one of the problems. And after line 20, pointer C's data is set to 1, and so because it is a union type, the next pointer is destroyed. So we need to decrease the reference count. And if we just see this example from our viewpoint, it seems obvious that we need to decrease the reference count here, but from the compiler's viewpoint, it is just a store of an integer type. So we need to perform some analysis to see if we need to decrease the reference count here. So summarizing the challenges, we first need to know where the pointers are stored, and we need to find the right instrumentation points, because if we instrument all the store instruction, then it will incur significant overhead. So this slide shows the overview of our approach. And first, we have a compiler plugin which instruments the library calls into the program. And we have a runtime library which consists of the function calls for managing the reference count. And then we have data structures. So first, for the data structure, we first have a pointer bitmap, which corresponds to the shadow memory of entire virtual address range. And a bit here indicates a bit here corresponds to the 8 bytes of memory. And if the bit is set, it indicates that the heap pointer is currently stored in the corresponding 8-byte memory region. And then we have a pointer to metadata map. that's just borrowed from the previous work. And what it does is that given a pointer, it gives an address of the location of the object metadata. And finally, the object metadata for each of the heap object, which includes a reference count and a few other informations. Now, for the runtime library, I'm only going to introduce 3 of the runtime library function calls and explain what they do. So first, the CRC alloc is called whenever the malloc is called, and when the object is allocated, they allocate the object metadata and initialize the reference count to 0. And also after that, we register the object metadata to the pointer to metadata map. And for the CRC store operation, it gets called, it's instrumented into the program before the store instruction. And here, we do not know if the pointer A was pointing to some other object. So we first check in the pointer bitmap if the heap pointer is stored previously in the pointer A. If the bit is set, we find the metadata for some object and we decrease the reference count for some object. And we free some object if the reference count is 0. After that, pointer A will be pointing to object A, so we set the bit in the pointer bitmap and we find the metadata for the object A, and then we increase the reference count for object A. At line 16, when there is a free operation, we call the CRC free function, and since the freed object memory region can contain the pointers, we look for the corresponding freed region in the pointer bitmap, and see if there are any pointers in object of the freed memory region. And we find the metadata for those pointers, and we decrease the corresponding reference count. And finally, we nullify the pointers in the freed memory region. So one more thing is that we free object B only if the reference count is 0. So by this way, one of the challenges introduced before can be solved. So one of the remaining challenges to find the right instrumentation point, and I'm gonna go over a little bit fast because I don't have much time. And so CRC store, we have some algorithm to determine if we are gonna instrument this store instruction or not. So instead of going all the details here, I'm going to introduce only 2 examples. So we instrument the store instruction in LLVM IR. So in LLVM IR, store instruction looks like this. So they have a value and a destination, and we have a type for the value and destination. And we first check if the value is the pointer type and instrument if it is a pointer type. And then we need to see even if the value is not a pointer type, we check if the value has been cast from the pointer type. So in this store instruction, we see that value is the I8 type, which is not a pointer type. But if we perform some kind of analysis, and we find this bit cast instruction, which casts the struct SV double pointer to I8 pointer. So what it's doing is that it's performing memcopy-like operation, which copies the pointers from the destination to the source region to the destination region. So we also need to instrument this instruction. So we do this kind of algorithm to find the right instrumentation point. So now onto the performance evaluation. We have compared our solution to several recent USF3 works, including Dangling and Oscar. And we have also compared our solution to the Boehm Dimmer's Visor Garbage Collector. And we use the benchmark spec benchmark and PARSEC benchmark and also web servers. We are not going to show all of the results here. And so why we are comparing with the garbage collector? It is actively maintained the C garbage collector, and it provides GC malloc and a few other APIs. And it automatically frees GC malloc object when there are no reference to the object. So in this aspect, it is very similar to our approach, but the difference is that they do not maintain the reference counts, but they only scan the memory periodically to see if there are no reference to the particular object and then free the object. They are not really intended to be used for the legacy C programs, but we found that they provide some options that we can use to apply it to legacy programs. So we've used that option to test garbage collector, and it worked for the most of the benchmark, but some of the C benchmark did not work using that option. And for the C++ benchmark, they didn't work. We need some manual work. So the runtime overhead, just summarizing our solution CRCount, which shows 22% on spec, which is about half the other Dangling and Oscar. And the Boehm garbage collector turned out to be really efficient for the spec benchmark, which we think that because they do not perform any kind of maintenance operation, but they only periodically scan the memory to free the memory object. And for the memory overhead, our solution shows very efficient compared to other approaches. And also the garbage collector here, since they do not free the object when the free function is called, but they need to wait until the scanning of memory, so they show a large memory overhead. For the PARSEC benchmark, which is a multi-threaded benchmark, our solution shows a similar overhead, but in terms of memory overhead, our solution again shows the very efficient performance. One of the aspects we need to see is since our solution delays the memory-free operation, we need to see how much overhead it causes. But we don't have much time, so I want to only say that the overhead caused by the quarantine zone is usually small. And since our analysis is not really 100% complete, we sometimes have memory leaks in some of the benchmarks. And so if you see the numbers, it is not really that big. It's almost negligible, but it can be critical for long-running software. So we additionally implemented a lightweight garbage collection using the pointer bitmap that already we have. So we did not add much to the performance overhead. And we also did a security evaluation, and we found that our solution successfully delays the memory reuse until the dangling pointers are gone. We have some of the limitations, and we need to manually insert one of the CRC-free cores before the custom memory deallocation. And so in the pointer bitmap, we assume that the pointers are aligned to the 8-byte boundary, but we encountered a few cases where this assumption does not hold. So in this case, we cannot track that pointers. And also, we have some limitations in the analysis. We only do the intra-procedural analysis. So when the pointers are cast to the integer before the passing to the other function and then stored to some memory location, you cannot track that operation. And similar to the data flow and the similar limitation. Right. So to conclude, it is hard to mitigate user after freeze efficiently, and we have come up with a solution that is efficient compared to the existing work by maintaining lightweight data structures and minimizing instrumentation points. So I conclude, and thank you for listening, and I'm happy to accept any questions.
Thanks. I'm Roland from NUS. Just wondering whether you encountered any problems with trading, because there can be some issues with trading.
Sorry, I couldn't hear.
Do you encounter any problems with multi-threaded programs?
Multi-threaded?
Yeah.
What kind of problems?
There could be race conditions. There could be race conditions in the...
race condition. So if you see our paper, there's some details about how we handle the multi-threaded environment, and we input whenever we need to modify the reference count, we use the atomic operations. So yeah, that adds a little bit of overhead for the multi-threaded. That's why we have a similar overhead with other solutions.